Thank you for the introduction, Mr. Chairman. So I am Alexandre Aubry from the Langevin Institute in Paris. I will talk to you about ultrasound. I'm one of the ultrasonic guy of the school, but I will show how tools we developed in ultrasound can be extended to seismology. And so I will start with a first slide showing the two media I will study in my talk, which is a volcano for seismic imaging and the brain for ultrasound imaging. And while these two media seems quite different in terms of length scales, kind of waves propagating through, I will show you that actually you have a lot of common issues to image a volcano or a brain in ultrasound. And you have some, and this, they can be studied in the same way because in both cases we are in a reflection configuration. We are building images relying on echolocation. We are investigating the wave propagating through these media thanks to array of geophones or transducers that can help us to probe the wave field at the surface of these media. And most of all, they are both very heterogeneous media, meaning that you have a lot of complicated trajectories of waves in this media, and so we need to, and for the brain imaging is a skull that is very difficult to go through. And I will show how we can solve these two issues with the same formalism, the matrix formalism. So just start to give you a very short introduction on the principle of echolocation. So in ultrasound imaging, what we have generally is a piezoelectric transducer that converts an electrical signal into a mechanical wave. So if we use only one transducer, we produce a spherical wave that illuminates the sample, which is made of scatterers. And these scatterers in acoustics, they are local variations of density and or compressibility. And then in reception, we record the backscattered echoes on the same piezoelectric transducer. And if we look at the signal as a function of time, the echo time, we have several, we see the signature of several main echoes that are due to the scatterers that are placed in front of the piezoelectric transducers. So we can build an image because we have a one-to-one association between the depth of scatterers and the echo time. And they are related together by the speed of sound. And this speed of sound, if you assume you know it in the surrounding fluid, then you can convert the time information into a depth information. Okay, so very simple thing. So now, how can we get an image? Meaning that we need also not only a depth resolution, but also a lateral resolution. So in acoustics, we use often array of transducers, so the same piezoelectric elements I showed you before, and these transducers allow you to control independently the wave field at each position. So you can send whatever wave you want, for example, a focused wave, by applying some time delays to the ultrasound pulse that you apply to each transducer. Okay, so that way you can probe the wave field, you can focus the wave field at a specific point, so then you get the lateral resolution. And in reception, you will record the wave field produced by this scatterer. It gives you this spherical wave, and then all these signals can be combined together by applying the same time delay as before in emission. You apply this time delay, you put all the signal in phase, and then you can sum them coherently to produce one pixel of the ultrasound image, okay? And then, if you scan this focusing law at different locations, you can retrieve an image of a liver, for example. So here, this is a typical image we obtain in ultrasound, where the brilliance is actually directly related to the local reflectivity of the medium. So this ultrasound image is based on the cofocal imaging configurations, meaning that we apply the same focus beamforming at emission and reception. And if you look at this image, you have different kind of structures that you are able to reveal. You see the interface at the beginning, the fat layers, the muscle layers, And then in the liver, you see you have some anechoic regions that are due to vessels. And in all the ultrasound image, you have also this what we call speckle, ultrasound speckle, which is due to the random interference between all the echoes produced by unresolved scatterers, meaning cells or extracellular matter that produce this random wave field. And I will show you how we can use this speckle to learn how to improve an ultrasound image, how to better focus ultrasound to get a reliable image of the reflectivity of the sample. So there are some hypotheses on which is based this beamforming process. First, homogeneous velocity C0 in the tissues. So generally, it's approximately the wave velocity in water, or a bit larger, but we know it. At least its average value. And we have also a strong hypothesis, which is a single scattering assumption, meaning that the wave is supposed to have encountered only one scatterer during its propagation through the medium. And this is, these two hypotheses are, of course, so if you check this hypothesis, then when you focus the wave, you produce a diffraction-limited focal spot that is only limited by the aperture of the transducer array. But of course, in reality, you don't check this hypothesis. You have a heterogeneous speed of sound, meaning that you have to go through several kinds of tissues that display a different speed of sound. You have also the problem of multiple scattering that can arise when you have strong heterogeneity, strong concentration of particles. And actually, this contribution has been neglected for a long time in acoustics, and actually it plays a big role in the image. And often, your speckle that you detect is not only produced by singly scattered echoes, but also by multiply scattered echoes, which can have a strong impact on the diagnosis that you can make. Okay, so when you have this problem, of course, your time delay law is not adapted to your medium, meaning that when you go through an aberrating layer, by aberrating layer I mean a different speed of sound compared to the propagation, the one considered in the propagation model, then you get wavefront distortion that produced an enlarged and distorted focal spot. And this gives a loss of resolution and contrast on the image. Sorry. Okay. And it can be even worse for transcranial imaging. So in that case, the ultrasound image looks like that. So you see that you have strong artifacts. Here it's a bright scatterer, and you see that there are several replicas. And this is due to the strong heterogeneity of the skull. So you have a strong difference of speed of sound between the skull and the brain. And you have also, of course, as you have this impedance mismatch between the brain and the skull, you have strong reverberations, multiples, as you call it in seismology. And of course, it gives you a strong artifact. So you see multiple reflections in the skull, but also these multiple reflections, you can see them for scatterers behind the skull. So this explains why ultrasound imaging is not often used for imaging the brain. You can do some Doppler. So Doppler means that you image the movement inside the medium. So typically you're imaging the blood flow, but the image is poorly resolved because of this problem, because you can only enter into the brain through this temp. And okay, it's a very small aperture array that you can use to do this thing. So in complex media, confocal imaging fails, and we need to find tools to go through the skull. So I will So I will go through different topics. I will show you how we can quantify and compensate these wave distortions in ultrasound. Then I will show you how these tools can be used to can be applied to passive seismology, and I will show you an application to the imaging of La Soufrière volcano of Guadeloupe. And then I will come back to ultrasound to show you how we can harness the spatio-temporal degrees of freedom of our measurements to compensate for the multiples reverberations and multiple scattering. And at the end, I will, if I have time, I will talk about dynamic matrix imaging, imaging of dynamic media. And then I will show you how we can exploit movement inside the medium to improve, again, the focusing process. And I will finish by quantitative imaging, meaning that the reflective image that we obtain in ultrasound, or just by echolocation, is a qualitative image. It only shows the architecture of tissues, but it doesn't give you some numbers. So in that case, we need to probe what we call the wave velocity and some scattering parameters to improve the diagnosis of some disease. And I will show you some examples at the end. I will propose some extension of this different improvement to some application to seismology. Okay, so let's start with the ultrasound. So in complex media, generally, historically, it has been studied in transmission, meaning that we have an array of transducers on one side of the skull, for example, and an array of transducers on the other side of the skull. So it's an academic experiment. We extract the skull from that guy. So and then we tried to do some experiments, some fancy experiments. It was in the 2000s. And then what you can do is to record what we call the transmission matrix, which is the inter-element response between each element of the array. Okay, so you use one probe as the emitter, and you then successively shot an ultrasound pulse from each element, and then you record the whole wave field. And this wave field, you see that it's a long coda, as Nicolai showed this morning. That is the result of all the complex paths that the wave can undertake inside the medium. So then, when you have recorded this matrix, you have all the information available on the medium. So what you can do, for example, you can do a Fourier transform, and then you obtain this transmission matrix not anymore as a function of time, but as a function of frequency. And in that case, you can relate very easily this transmission matrix relates the input wave field with which you illuminate the medium to the output wave field. And once you have this transmission matrix, you can, by inversion, know the exact input field you should apply on this array to get a specific field on the other side. So it has been widely used for focusing through complex media, for detection, or for even communication in the electromagnetic community, but it's not really adapted to imaging. Okay? Why? Because in imaging, we are most of the time in a reflection configuration. So in that case, we can still emit a pulse by each element of the transducer and record the backscattered wave field. And this reflection matrix contains all information available on the medium. But still, what you need to image the medium is you can perform some target detection by just performing a singular value decomposition of your reflection matrix in multi-target media. You can find the wavefront that focus selectively on each bright scatterer of the medium, but still you don't image, you only selectively focus on one point. So it's good for therapy, for example, if you want to burn some parts of the brain because you have some problems. But if you want to image, you need to access to what we call the transmission matrix inside the medium. So you need to find the Green's function between this point, for example, and any virtual detector inside the sample. And once you have this transmission matrix, then you're able to unscramble all the multiple scattering paths you can get through the complex medium, and you are able to image your behind the skull, image the brain. Okay, so generally what we acquire the reflection matrix in a canonical basis, meaning in the transducer basis, but it can be measured in many bases. And based on this reflection matrix, what you can do is do exactly in post-processing the focusing operation I described at the beginning of the talk, the focus beamforming at input and output. So this is done by just considering the sum over U in and U out, so the transducer at input and output, of the reflection matrix coefficient. These reflection matrix coefficients are complex because we are considering the IQ signals. And I'm just considering this reflection matrix coefficient at specific time that corresponds to the time delay we applied initially on the ultrasound scanner to focus at a specific point at in. And I can apply the same time delay at output to describe the propagation of the wave field from the scatterer to the transducer array. And at the end, I obtain this kind of this kind of image. So here it's an image of an ultrasound phantom we often use in acoustics. This ultrasound phantom is mimicking the tissue properties. And on top of that, so it gives you speckle, random reflectivity due to the random distribution and unresolved scatters. But on top of that, you have some specific bright points that allows you to assess the focusing, the length, the width of the focal spot. So here we don't have any aberrations, so the image is perfect. You have also this bright cylinder that gives you a larger reflectivity of the speckle at some specific location. And like that, you can also assess the contrast of your image. Okay, so when you add an aberrating layer on top of the phantom, this is what you obtain. You see that you have on the bright scatterers, you see the width of the focal spot that is enlarged, so you see the effect of the aberrating layer. But most of the time in acoustics, we don't have these bright scatterers, and we can only rely on the speckle. And on the speckle, it's difficult to see if you are aberrated or not. The speckle statistics is random, and you cannot see just by looking at the image the effect of an inaccuracy of the speed of sound model. Okay, so what you can do then, if you want to probe the quality of focusing, is to go beyond the confocal configuration and now to focus on different points inside the medium. So you decouple the input and output focal spots. And like that, you can build virtual sources and virtual detectors in your medium, and you get what we call a focused reflection matrix, so a reflection matrix that is not defined anymore in the transducer basis, but in a focus basis. So it contains the impulse response between a set of virtual sources and receiver inside the medium. And in a phantom with no aberration, this is how it looks like. So it's a reflection matrix that displays a strong diagonal signal, and this strong diagonal signal is a confocal signal. It's when you focus at one point, you only collect energy backscattered around the same point. Okay? So with this diagonal, you retrieve. So this is the way you're doing it. You're just applying different time delays at input and output. One to focus on R in at input, and one to selectively enhance the signal coming from R out at the output. And you're considering just the ballistic time, the way and return echo time, so based on the single scattering assumption. So this is so when you have this image, you can just by considering the diagonal of the reflection matrix, you get one line at one specific time of light. You get one line of your image. Okay, but now if you're considering the off-diagonal elements, they give you an information about the focusing quality. So, for example, if you have an aberrating layer, remember that the speckle statistics was difficult from the speckle to understand if you are aberrated or not. If you look at now at the focus reflection matrix, you have a direct information of this bad focusing because you have a spreading of the energy. You can probe the spreading of the energy across the focal plane. When you try to focus at R in, you have an enlarged focal spot, and then you can probe this enlarged focal spot with the virtual detector that you have created. You scan this virtual detector, and it gives you this focus reflection matrix that is very aberrated. So now the idea is to compensate for those aberrations, just relying at the speckle signal. So to do that, to compensate for aberrations, first we need to go 3D, because aberrations generally in the skull, or we'll see after in the volcanology, we have a 3D distribution of the speed of sound or the wave velocity or the seismic wave velocity. And so if we want to properly compensate for aberrations, we need to use matrix array of transducers, so 2D distributed array of transducers. And here I put just an aberrating layer that is made of muscle and fat. They display very different speed of sound, and you will see that it alters the ultrasound image you can build with this system. So this probe is 32 by 32. Yes?
Is it possible to go back one slide?
Yes. Yes. Okay, so this image is just made by considering the confocal signal, meaning just the diagonal of the reflection matrix. the diagonal of this focus reflection matrix at one depth give you one line of this image, okay? And then if you produce this focus reflection matrix at different depth, you have the other lines of the image, okay? So generally, when we build an image, we only use the diagonal elements. And what I will show you during this talk is that you have a lot of information by considering the off-diagonal elements, because this is where the aberrations are, this is where the reverberations, the multiple scattering signature is. And if you want to compensate for this phenomena, you need to investigate these off-diagonal coefficients. Yeah, it's not. So generally, we only look at that, and what I will show you is that it's very important to look at afocal signals. Okay? Thank you for the question. So we have a probe. We have an ultrasound platform that allows you to record this reflection matrix. And then, if we look at the focus reflection matrix, so you can do exactly the same thing as before. In 1D, it gives you this kind of reflection matrix with a diagonal and off-diagonal coefficients that probe aberrations and multiple scattering. But then if you go to 3D, then your matrix is more complicated. You have a matrix of matrix, so each submatrix is the response between one line of transducers and another line. And then you have many of them, and you can store everything in a huge reflection matrix that probe the whole response of the medium. And from this huge reflection matrix, what we can do, we can, as before, build a confocal image of the medium, so that you obtain a three-dimensional image, and already you see some distortion on the neuron rods that are a result of the aberrating layer I introduced between the probe and the phantom. So now, if you look at the off-diagonal elements, now these off-diagonal elements give you a 2D wave field, and this 2D wave field is the focal spot that you have probed by focusing at one point and scanning the wave field around this focusing point. So it gives you an information about the focusing quality. So here the focusing quality is not so bad, but we see we have some secondary lobes here that will produce some aberrations on the image. And this reflection, actually this what we call reflection point spread function, is the result of the convolution between the input focusing pattern, the point spread function produced by the input focus wave field, and the output PSF. And so in a reciprocal world, these two PSF are supposed to be the same, but often in acoustics, we are not recording the full reflection matrix, meaning that we are acquiring, for example, the reflection matrix with a plane wave basis. So this reflection matrix is not perfectly symmetrical, and so that's why we are decoupling the input and output in the PSF. Okay, so now I can have this information locally, meaning that I can look at the focusing quality at different points at a specific depth, and you see that you have a strong evolution of this PSF across the medium. So behind the muscle, you have a diffraction-limited focal spot, because we took as a wave velocity model the velocity of the muscle, the speed of sound in muscle, but in the fat layer, you see you have strong aberrations, and so you need to compensate for aberration locally. And of course, you see that compared to the diffraction limit, you have a huge spreading of the backscatter decoys beyond this the expected focal area. So to improve the focusing process, we will come back to old tools that have been developed originally in astronomy and has been transposed then in ultrasound imaging in the 80s. So the idea is the following. So if you apply a time delay law, it goes through an aberrating layer, then you get strong distortions, an enlarged focal spot. Okay, so now if you're able to find, so the goal is to find the delay law that perfectly compensates for these aberrations, such that it produces a perfect spherical wavefront behind the aberrating layer and perfectly focus at the targeted point. So how to retrieve this focusing law? So in astronomy, we have stars in the sky. They are point-like sources for us. In ultrasound, you can have sometimes some bright scatters, and you can use them. So you shine the medium with a specific wave field, and then you have an echo that is very strong. And if you look at the echo, it has some distortions induced by the aberrating layer. And if you time reverse, this wavefront, you get the focusing law, meaning that because the wave equation is invariant by time reversal, the wave will experience the same trajectory as in the past, and you will produce a perfect cylindrical wave that will focus on this bright scatterer. Of course, we are not often in this situation, and what we have in ultrasound imaging or even in seismology, often we have a distribution of scatterers, okay? It means that we retrieve a focused wave field that is modulated by the random reflectivity of the medium and also by possibly some multiple scattering events that take place between the transducer array and the focal plane. So in that case, we need some averaging, okay? And to do the averaging, what we can do is to focus at several points close to the first one. Each time we obtain a different wavefront, and these wavefronts are tilted between each other because they come from different specific points, okay? And so what we can do is to realign these wavefronts. I will show you what I can do after. And we can cross-correlate these backscattered echoes to get what we call the coherent wave. And this coherent wave will allow you to find a focusing law as you had created a coherent virtual scatterer from all this realization of different focal spots at input, okay? Okay, so this, when we have this aberration law, then we can sum it to a geometric component that is dictated by our wave velocity model, and we have this focusing law, a phase law, that we can apply, or a time delay law equivalently, that we can apply to focus through the aberrating layer, and then by changing the geometric law, we can address other points close to the first point, okay? And it works in a specific area called the isoplanetic area, which is where, from this region, for all these points in this region, they see approximately the same aberration, and so we can apply the same aberration law to focus through the medium. But of course, if you go too far, this point will not see exactly the same aberration law, and so the original law is not good anymore, and you need to learn the aberration law for each isoplanetic area inside the medium. And this isoplanetic area can be quite small. It can be a few millimeters in ultrasound. So we need to estimate actually the response between each pixel of the medium, each pixel of the image, and each transducer. So to do that, so of course, this explains why adaptive focusing that has been developed in astronomy has not been used for a while in acoustics, because actually it was very difficult to implement it physically. Because in ultrasound imaging before, we used to focus physically in the medium, and so we need to focus physically all this operation I described before. We need to do it physically for each point inside the medium. So it's very time-consuming, and we cannot have time to do all these operations. And on top of that, of course, the medium is moving and everything, so it was not practical. But now we have the reflection matrix tool, meaning that we can record the reflection matrix once, and then we can apply all these focusing operations in post-processing. So it gives you a high flexibility, and we can converge towards an estimation of the transmission matrix between the transducer array and each point inside the medium. And we can iterate the process to improve the formation of the virtual guide star. So one question about this T-matrix estimation is the correlation area, the area that you need to consider to converge towards a good aberration law, because you need to smooth out the fluctuations of speckle and of multiple scattering. So you need to take it small enough to check the isoplanetic assumption, but large enough to converge. And so if you look at the error made on the T-matrix estimator, it can be expressed as follows. So you have a first, sorry. So this is the error between the real T-matrix and the estimator, and it is inversely proportional to what we call the coherence factor. It's a focusing quality, so it goes from 0 when you are not well focused, and 1 when you are perfectly focused. And so, of course, it will play, it actually quantify the blurring of the guide star. And then you have the NW, which is the number of resolution cells you have in your box, in the correlation area. And so if you consider, so you can consider the aberration phase law that you record for this point, and as a function of the box that you consider to perform the correlation between the different wavefronts, the distorted wavefronts. And you see that you have a very different signal depending on the size of the box. And the idea is to understand, to know when this aberration law, we can be confident in it, when the number of points is sufficient to sufficiently average the effect of speckle, the random fluctuation of speckle, and multiple scattering. So this convergence can be controlled actually by looking, because we are doing an iterative correction, so we are considering first the correction at input and then the correction at output, and look at the aberration phase law. And what you see is that at the beginning, the two laws, when the box is small, are very different, but when you have a sufficiently large box, you see that you have very similar aberration law, and then based on spatial reciprocity, you're sure that you have converged towards a good, satisfying resolution law. Okay, so we monitor, sorry, I didn't show you. So we consider the scalar product between these two laws, and we see that after, for example, 2 resolution cells, we are sure about of aberration phase law. So based on that, we can, based on this feature, we can have a strategy that consists in gradually reducing the size of the isoplanetic patch. First, correct the low-order aberration that are the most isoplanetic, and then improve the coherence factor, reduce the size of the guide star, such that we can address more high-order aberration. And this is what we do here. Just by considering smaller and smaller patches, we have a more detailed description of the aberration law, local aberration law, and you see on the point spread function that now at the end we have a diffraction limited PSF everywhere. So we can now build an image based on this T-matrix estimation. So you see that you are able to compensate for aberrations. You see it on the bright scatterers where you had several secondary lobes that are now resolved, and you have a better contrast on the image. And so you see it also on the reflection point spread function give you this information also by looking at the off-diagonal coefficients of the reflection matrix. You see that now you have a diffraction limited focal spot everywhere. Okay, so now let's move to transcranial imaging. So transcranial imaging is more complicated because the aberrating layer is not anymore just one muscle part and a fat layer. It's more complicated. You have strongly varying laterally aberrations. And so we still, on top of that, you have a strong attenuation. So what we do for the attenuation is to record the reflection matrix not anymore in a canonical basis, but as I told you, in a plane wave basis, meaning that we are now we are illuminating the medium, with a plane wave, with a set of plane wave that allows you to get a higher signal-to-noise ratio. And on top of that, you can also speed up the measurement of the reflection matrix because often only a few sets of plane wave are required to get all information needed for imaging the medium. So if you look at the reflection point spread function that we have in the brain through the skull, we have very complicated reflection point spread function. It's very distorted by all the heterogeneities of the skull. And if we get aberration laws in this medium, we see that it seems that we have some deterministic Fresnel rings in some parts of the field of view, but in other parts, we have a very noisy aberration law that is due to the imperfect convergence towards the transmission matrix. Okay, so, and then you can detect that by looking at the spatial reciprocity that is not at all checked in that situation. So what we can do is to filter the high order aberration by applying a confocal filter. So I smooth out the RPSF, and at the end, I obtain a reflection point spread aberration law that are not perfect, but at least they are physical, and you can use them to compensate for the low order aberrations. So you can do that at every depth inside the medium, and so you have the original PSF and the corrected PSF. So it's not perfect because we don't have enough isoplanetism to compensate for all aberration, but at least we have removed the low order aberrations. And so the resolution is improved still by a factor 8. And we have an image, so I show you the bright scatters that we had in our head phantom, and you're able to resolve them much properly than at the beginning. So it's still encouraging. And that's why we moved then towards in vivo measurements in the next part of this first part. So now we want to do in vivo transcranial imaging. So to do a transcranial imaging, we need to work at low frequency because we have strong attenuation, but it means that we have a poor resolution, meaning that 1 millimeter at 1.5 megahertz is not enough to image all the vasculature network that you have in the brain. So what you can do, and what has been done a few years ago by Olivier Couture and Michael Tanter at the lab, was to use bubbles. So we inject microbubbles in the blood, and these microbubbles will act. It's not painful. Don't worry. We inject microbubbles, and these microbubbles will work as point-like scatterers, isolated point-like scatterers, and we can use these bubbles to make ultra-fast movie. So we will see the bubbles moving inside the brain. And because they are very small and isolated bubbles, when we image them, yes, we image them if we are in a good situation with a focal spot whose size is dictated by the diffraction limit, but you can localize them at the maximum of this PSF, and so it allows you to go well beyond the diffraction limit, and typically you can improve the resolution by a factor 10. And so then by tracking these bubbles, you can rebuild the vasculature network inside the brain. And so it's very useful for functional imaging and for stroke detection or diagnosis. And so this is the kind of image you obtain. Here it's in the small animals, so the skull is very thin, so we don't have problem of aberrations, but you have all the nice feature of the vascular network inside the brain of small animals. So now, if we want to go towards human transcranial imaging, then it's more complicated because you have the skull, and the skull is inducing a lot of aberration. So the image is not so nice, but still, of course, you need to have access to a matrix array of transducers so that you can control all the aberration in 3D. And so, of course, you don't have anymore an ideal PSF, but now you have an apparated PSF, an enlarged focal spot. So it means that when you do the deconvolution, when you try to detect the bubbles, you will have the feeling that you have detected 3 bubbles instead of 1, and the signal-to-noise ratio is much weaker, of course. So you have a bad localization, so you can compensate these artifacts. So you see you have duplicated vessels. So there have been some studies with deep learning, and they showed that they have a nice correction of their image, but we took a more physical route towards this correction by combining this ultrasound localization microscopy with matrix imaging. So what we do, so it's an experiment on the ship first, just to try. Then what we do, so it's a collaboration with Olivier Couture's team in Paris, and the idea is the following. So we first have a reflection matrix acquisition that is quite long because we need to have access to all the spatial degrees of freedom to get a nice estimation of the transmission matrix inside the medium. And then we inject microbubbles. Sorry, it doesn't work. We make an ultra-fast movie acquisition, and then, sorry, we use the aberration laws that we learn from the reflection matrix to improve the detection and localization of bubbles. So, sorry, I come back. So first, this is the initial image that you obtain in the brain. So you improve with the matrix estimation your B-scan image, but then it's poorly resolved because you are at low frequencies, and so then you use bubbles to improve the imaging. So we correct the reconstruction of the microstructure of the image with bubbles by first detecting better the bubbles, because we have a better focusing process inside the medium. Everything is in post-processing. And then you can remove some artifacts that I showed you before, where you detect street bubbles, whereas when you have compensated for the aberrations of the skull, detect only one bubble, and you can track them throughout the experiment. And then you get a better image. So here, what you image here is the Willis circle. This Willis circle is a crossroad of blood inside the brain, and you can remove some artifacts. For example, in this situation, I will show you after, once the movie has finished. Yes, you see some duplication of this vessel that now you have resolved, and you have plenty of blood vessels that are revealed by combining matrix imaging with ULM, the ultrasound localization microscopy. Okay, so this matrix imaging tool is very convenient to improve the image in ultrasound, but it can be also applied to every field of wave physics where you have an array of sensors that probe a complex medium. So it has been developed in optical microscopy in my group, where we image an opaque cornea. So it's a B-scan of an opaque cornea. If you use conventional methods, such as optical coherence tomography, which is equivalent of ultrasound for light, you see that your image is poorly resolved, and you don't penetrate inside the cornea because it's very complicated. Here, the thickness of the cornea was 10 scattering multiply path, meaning that the wave has to go through 10 scattering events before reaching the bottom of the cornea. Whereas with matrix imaging, you're able to estimate the transmission matrix for every pixel inside the medium, and you're able to, in post-processing, to compensate for all the forward multiple scattering events that take place inside the cornea and reveal the image over the whole thickness of the cornea. And of course, we can apply it to seismic imaging, and this is something that we have done with Michel Campillo and Rita Tuma, where, for example, we apply it to the San Andreas fault zone with a dense array of geophones. If you perform a confocal image with your data, this is the kind of image you obtain, an image that is totally blurred by the wave velocity variations. So here it was with P waves, and so you're not able to retrieve the details of the fault area, but you can apply all your tools that I just described, the matrix imaging tools, to reveal the damaged area and then the position of the fault in depth with different geological units on each side of the fault. And this image was quite puzzling because the resolution was actually much better than expected. Actually, the resolution, if you look at the reflection point spread function, was almost lambda over 2 everywhere, whereas normally, in the usual world, your resolution is decreasing with depth because it's related to the wavelength times the depth divided by the geophone array aperture. And that's why we thought about this mechanism. And I will show you the answer, the reason for such a good resolution in the next part. So just to conclude, so we have common issues of universal formalism, but the current limits are the following, and I will try to answer to this to overcome these limits. It's only qualitative, as I showed you. It's only a reflectivity image, and I will show you how we can probe the wave velocity, make a tomography of the wave velocity based on the focusing laws that we have determined. We only capture the low-order aberrations because we are relying on the memory effect that is often not respected in complex materials such as the skull or the volcanoes. We had a dense array of sensors, so the idea was to extend this idea to sparse array of sensors and see if the method is still working in that case. And we have this high resolution that we have observed with Michel in San Andreas, and we wanted to understand better this phenomenon and see if there are no artifacts, if we can be really confident on this image. So to do so, we have used data that have been collected by Arnaud Burtin and Jean-Christophe Komorowski from the IPGP in Paris, Institut Physique du Globe de Paris. And all this work has been done by Elsa Giroda, that I thank for the slides. So you know everything about this. I will not repeat all the nice introduction made by Nicolai, but here I will only consider the P waves. But all of what I will show you can be also extended to S wave. You can combine S wave, P wave, and S wave. So we are using bulk waves, okay? And we show you how we can use bulk waves to perform an imaging in depth based on the correlation measurement we made here it's active experiment, but we show you that we can use also the cross correlation of seismic noise to record the reflection matrix and build an image based on the P wave contribution contained in this reflection matrix. But of course, you can also apply these algorithms to perform imaging with Rayleigh waves. This is something that we have not done, but it can be done. And if you are interested, we can discuss about this kind of thing. Okay, so active seismic imaging. So normally, in the old world, before Michel Campillo arrived, we used to do it like that. So we had a vibrating truck that emits a seismic wave inside the medium. You have some scatterers or some layers that reflect the wave field, and then you record this wave field, the reflected wave field, with geophones. Okay. So now, if you do that, if you repeat this operation for several positions, of the truck, then you get what we call the reflection matrix, time-dependent reflection matrix, and all the Earth response is stored in this matrix. And then you can post-process it, and so the situation is exactly what you find in ultrasound imaging, where you shot ultrasound pulse from a piezoelectric transducer, and you record the reflected wave field for any position of the source. Okay, so once you have acquired your Earth response matrix, what you do in seismology is migration of echoes reflected in depth, and it's perfectly analogous to numerical focusing I showed you in ultrasound imaging. So of course you need a wave velocity model, and your image depends on the accuracy of this velocity model. So you can have a satisfying spatial resolution if you have a good wave velocity model, but the penetration depth is limited because you cannot emit so much energy with this kind of source. It has, of course, an environmental impact. It's expensive, and it's not suitable for steep regions such as volcanoes. So the alternative is, of course, the passive imaging method that has been introduced already by Nicolai, so will be very fast. So you can use the noise sources, wind, precipitation, ocean, volcanic activities, or the anthropic activities to record a seismic noise on 2 points. And then if you have been at the school, you know that you can record this noise at 2 points, and if you cross-correlate this seismic noise, it will converge under certain conditions that Nicolai explained towards the Green's function, meaning the response between point A and point B. So you have the causal part, the anti-causal part. In one case, A is the source, in the other part, B is the source. But this Green's function is exactly what we measure when we do an active experiment. And so at the end, what you obtain is the reflection matrix I told you about at the beginning. Okay, so it's very flexible, etc. So now, once you have this reflection matrix, the signal contained in this reflection matrix, at least for the bulk wave contribution, contains several kind of components. First, the specular reflections on the layer between the different geological units, but you have also local variations of density and elasticity. So it can be, for example, in fault area, it will be the fractures between rocks. In volcanoes, it will be magma fluids that can induce a scattered wave field. And this is this scattered wave field we must exploit to image here the volcano. So we have a propagation model that we can use. And of course, the image that we build at the beginning is based on the same assumption that we do for ultrasound imaging. But of course, you can have, in reality, multiple scattering, the long coda that you saw before, that can hamper wave focusing inside the medium. You have also some aberrations, longer scale variations of the wave velocity that introduce phase distortion on your signal, and that will introduce some strong aberrations on your image. And you can have also multiple reflection, exactly as in the skull for ultrasound. So common issues. So we can now solve, and of course you cannot rely on the depth, the relation between depth and echo time because of these issues. So now the idea is to exploit matrix imaging. So this is done here on this array of 76 geophones that is quite sparse. Still you have an interstation distance which is roughly lambda over 2, because we are working in the 10-20 hertz bandwidth. So we can do the correlations of the seismic noise that has been recorded over 2 months on top of the La Soufrière volcano. And we, at the end, when we do the correlation, we only consider, for example, the causal part, and we can average the causal part and the anti-causal part, and we get the reflection matrix exactly as in acoustics, except that the geophone's distribution is more complicated and it's sparse. But still, you can perform some numerical focusing. So we apply time delay laws on our reflection matrix, and we can simulate the experiment where we focus a wave at a targeted point R in as a source, and we and at the output we can extract the signal coming from a virtual detector at R out. So we obtain a focused reflection matrix based on the existing velocity model. So here is an integrated wave velocity model, but we can use more complicated wave velocity model. As you will see, our method is quite robust with respect to the wave velocity model, so this is why we can do this kind of assumption, very strong assumption. Okay, so the focused reflection matrix looks like exactly we had in acoustics. We have signal along the diagonal of the small matrix here, but you see that you have a very large enlargement of the signal along off-diagonal coefficients, which is a manifestation of the aberration. So this is a kind of matrix, submatrix that you obtain. And if you look at the diagonal, you can get the confocal image of your volcano at a specific depth, here 1.6 kilometer. But you can, so you can do that for every depth, and you get this kind of longitudinal cross-section, and this image is very poor. You see that you have some random fluctuation, but you don't see anything very interesting in this image if you just look at a confocal image. Now you can, thanks to the matrix approach, get access to the reflection point spread function, and you see that you have a lot of energy that is backscattered outside the diffraction limited focal spot. And here's the reflection point spread function, because we are in a sparse medium, meaning that we are isolated scatters, we'll see at the end. It's just the product between the input PSF and the output PSF, and in that case they are strictly equal. So we have a direct access to the transmit PSF looking at the reflection point spread function in that situation. So the inaccuracy of the wave velocity model, as I said, hampers the wave focusing and prevents from the visualization of the volcano internal structure. So this is the kind of image you obtain. You have the PSF at different locations, and you see it's awful everywhere. And so now what we can do is play with this reflection matrix, as I showed you before. So first, we project the data in a new basis. So I go from R out to U out just by using a propagator that allows you to look at the reflection matrix between the focus basis and the Earth surface basis. So this Earth surface basis is a virtual, dense and regular geophone network that we consider at one specific location, which is approximately the Earth's surface. And then I look at the signal that we record. When I focus at one point, I get a reflected wave field. When I focus at another point, I get another reflected wave field. And these wave fields are tilted with each other because we are focusing at different points inside the medium. So then what we can do is to extract the aberration part of the signal by removing the geometric component that is expected according to our wave velocity model. Okay, so if you do that, we build what we call a distortion matrix, meaning that we have realigned all the wavefronts together. And from the focus basis perspective, it's like we are descanning performing an angular descan of all focal spots, and all these virtual sources that I plotted here are now virtually located at the same location. And based on that, we can now extract some correlations between the different realization of the input focal spot and synthesize a virtual coherent source like we have in astronomy, and we can extract the aberration phase law due to this aberrating the fluctuation of the wave velocity inside the medium. So, for example, at a specific depth, 1.6 kilometers, this is the kind of aberration law we obtain. And this aberration law is related to the wave velocity anomaly that you have at the surface, just close to the surface of the volcano. So you see the distribution of geophone, and you see that we have information also outside this virtual geophone position, and this is the result of refraction inside the volcano. Yeah. Yes. Nothing more. Very simple. Yeah. Yes. Yes, yes, I will show you after. Yeah, but yes, yeah, there are plenty of things. Here already, if you assume that you have only aberrations at the top, can relate the phase with the wave velocity anomaly that you have. I will show you some strategy we have to extract this wave velocity anomaly. Okay, so now I can use this transmission phase law. I can phase conjugate it. It's the equivalent of time reversal in the frequency domain. And then I can compensate for the aberration induced by the wave speed heterogeneities and retrieve a nice focal spot at each point. And based on that operation, I can correct my confocal image. And you see that we already, so you have different aberration phase law at different depth. You have different transverse cross-section at each depth. And you see that your image now shows a nice chimney, at least for the first 4 kilometers, you're able to resolve this chimney. Beyond, it's more tricky to find anything, and it's because the resolution is not so good here, because you're limited by the geophone array aperture, which is quite fancy, and so you have focal spots that are not very focused. But still, on the reflection point wave function, you see that you have some enlargement of this focal spot, and this enlargement is due to the geophone array aperture and the depth that controls, that dictates the resolution for this kind of methods. But you see that on the RPSF you have also some phase, and this parabolic phase law will be interesting, we'll see in the following. This parabolic phase law is a result of the curvature of the wavefront, because we are not in the far field, we are in an intermediate field, so you have this kind of parabolic phase law, and this parabolic phase law adduces some spatial frequency, high spatial frequency contents that you can exploit to improve the resolution in the following. So here I just show the comparison between the initial image and the new image. So you see it's already nicer. But now let's see how to improve again the resolution at in deeper region. And to do that, we will analyze now the wave field, no more in the Earth surface basis, but in a plane wave basis. So you can project your data from the focus basis to the plane wave basis just by performing a spatial Fourier transform. And then when you look at the distortion of your wave field, it's like you're descanning now laterally your different focal spots. And now you see that the signature of your different reflectors that you had in the underground will emerge on different parts of the spatial frequency spectrum. So it means that now we are completely different than before. We now have a perfectly anisoplanatic signature, meaning that for each scatterer position, we have a very different distortion, and actually even this reflected wave field project in different parts of the spatial frequency spectrum. But this will allow us to control the wave field differently, independently, when we want to focus here, here, or here. And so based on that, we can address independently each scatterer, each location inside the volcano. And on top of that, we have this parabolic phase law I told you about. And this parabolic phase law gives you access to a larger spatial frequency content than before. You have Fresnel rings, and you see that the focusing law that we extract in the key space, so here it's in the key space, so you have the angle so the support here is K0, so it's the wave number associated with the P wave. And you see that normally all the signals should be contained in this diffraction limited support due to the finite size of the geophone array, but you see that you have a lot of signal outside, and this is the result of the Fresnel rings generated by this parabolic phase law. And so we use this phenomenon to get a much fine resolution in depth. So of course it works only if you have few scatterers inside your medium. It will not work in speckle, but still if you have a few scatterers, you will be able to address them at the same time. And you obtain now an image of the magma storage system in depth. So you have the chimney, and then you have, our hypothesis is that we are imaging the magma storage system in this region. So if you look at of course, and you see on the RPSF, you have now a resolution which is much better than the diffraction limited resolution. So if you look at the image, so here it's the initial confocal image, now the matrix image. So you see we have some kind of lenses that are linked together by a vertical conduit in the magma storage system, and you have the chimney in the first kilometers that we already revealed at the first step of the system. You can do some isosurface representation. It's always a bit tricky, but you still see some arrangement of horizontal lenses inside the magma storage system. And this is very nice because we can make some comparison with the conceptual views that have been proposed by volcanologists in the literature. And it seems that we don't have a unique magmatic chamber in this volcano, but more vertically arranged pile of lenses of magmatic mushes. And of course, we need to continue to analyze these images and use the dynamics of the volcano to perform a much better resolved image of this magma storage system, so that you can see the movement of fluids inside the volcano. But this kind of image are completely new for volcanologists. At least they seem quite very enthusiastic about this kind of image that shows a resolution of 100 meter until 10 kilometers. So it's very nice, a very nice view of the volcano. Of course, so it can. So as I said before, we can revisit the results we obtained with Michel and Rita in the San Jacinto, California fault, where we had a very nice resolution, and this is exactly the same phenomenon that explains the high resolution we obtained. And we also applied this method at a much larger scale in the 0.1, 0.5 Hertz for the North Anatolian fault, and we have been able to reveal the different geological units you had below this geophone array. We are able to reveal the MOO and the extension of the damaged fault, the North fault in depth. And so it's just to show you that this method is very general, and you can apply it to any scale, provided that you check more or less the Nyquist criterion, meaning that the distance between your sensors should be approximately λ/2. This is the limit, okay? Okay, so now we can move towards more complex things. So just to tell you that this method is very robust to data quality and rough velocity model, in contrast with full waveform inversion. So it's a more physical route towards imaging in depth the Earth. But of course, the two methods can be also are complementary, meaning that you can have a first guess on the velocity model using matrix imaging, as I will show you after, and then you can introduce it in the full waveform inversion scheme and improve your image. And of course, here it has been very limited in terms of model, because we only use a scalar model. So then you can perform a more complex. You can use a more complex propagation model tool to build image based on both P wave and S wave. Take into account mode conversion. There are plenty of stuff to do if you are interested. But the main problem from my perspective, acoustic perspective, is that you have no compensation of wave velocity dispersion. That can be huge in seismology, I guess. And you can have a lot of reverberations also, as I showed you in the specific example of the skull, but I guess you can have the same problem in seismology, of course. So now I come back to acoustics to treat this problem, because we always start from acoustics, where we can have very well controlled experiments, as said by Nicolas, and then we can try to extend to more complex situations like yours in seismology. So we will try to compensate for the multiples. So I come back, I don't know how many time I have, it's okay, 20 minutes? We start late. Okay. So we're only on 106 slides, it's okay? Okay, so if you want to, I go slower, up to you. tell me. So I come back to this academic experiment, the phantom. We build an image, and when we have a good wave velocity model, we have a perfect match between what we call the isochronous volume, which is dictated by the time of flight we are considering, and the focal plane we are focusing, and the two are coincide. Now, if you add a plexiglass layer between the probe and the ultrasound phantom, this is what you obtain. The confocal image is awful because you have a lot of reverberations inside the plexiglass layer, and you have a lot of artifacts behind each bright scatterer, and this is due to the multiple reflections that you have in your system. Okay? So you have a defocus, which is due to the mismatch between the wave velocity model and the real speed of sound distribution, okay, for the ballistic, even for the singly scattered wave, or the ballistic wave. And you have also the multiple reflection, as I explained to you. So we need to compensate for all these phenomena. Okay. So now what we will do is to go beyond just a spatial analysis of the focus reflection matrix. So before, we only considered the focus reflection matrix at a given specific time of flight. Now I will add in this formula, a tau, which is the lapse time between the ballistic time and the real time you will consider. Okay? So now you illuminate the medium with a focused wave, you collect backscatter echoes coming from another point, but you let the wave propagating between these 2 points. Okay? You're considering, you go beyond ballistic time to probe for multiple reverberation, multiple scattering, and all the stuff. So if you do that in a very simple configuration where you don't have any aberration, you're able to extract from this focus reflection matrix a movie of the wave inside the medium. So here I just consider one specific point on a bright scatterer, and you see you're able to image the focusing process inside the medium. Why? Because you have speckle everywhere, and this speckle, you can use it as microphones distributed everywhere, okay? But here you have a real source, which is your bright scatterer. So what happens now when you are in speckle? Sorry. So when you are in a speckle, this is the kind of movie that you obtain. So you see you have still a wave that is propagating, but you have a lot of mess on top of it and behind. And this mess is due to the random fluctuation of speckle, but also of multiple scattering events that take place between the probe and the focal plane. So you need some averaging to remove this kind of incoherent phenomena, incoherent in this in that perspective, but they are still deterministic. So you can use now multiple realization of the disorder by looking just on one isoplanetic patch, considering several sources in a specific area. And if you perform a correlation between all these movies, this is what you obtain. So you're able to retrieve the signature of the coherent wave, okay? As we add just one bright reflector at the center of this window. So this is very nice. So now we have a self-portrait of the focusing process exploiting speckle. So now if we use, and you see here, of course, we are in a perfect situation. So we have the focus wave we expect, that is focusing just right at the focal plane at the time we expect the ballistic time. But now if we use the same, we consider the same movie in the phantom plexiglass experiment. So you have this coherent wave, and what you see is that behind, you see a lot of mess, and this mess are the multiple reverberations you're trying to compensate for. So now we have access to, thanks to the focus reflection matrix as function of time, to the ballistic wave and its defocus, because it's not focusing not anymore at delta z equals 0, but at another location. But we see also all the long temporal tail of echoes that are due to reverberation. So we can use this information to compensate. So this is the kind of thing that we are recording. Okay. Okay. So now we have this. We are able to probe the temporal dispersion of the wave across the medium. So you have the ballistic wave. You have the first reflection, second reflection, etc., etc. We can perform a Fourier transform. It gives you an aberration, a reverberation phase law. If you look at the modulus, you see a kind of oscillations that are Fabry-Perot-like behavior. Okay, you have some frequencies that are more transmitted than the others, but still we can use this reverberation phase law to compensate for the reverberation inside the medium, and you obtain an image that is not much better. You are able to retrieve the first scatterers that were completely hidden in the mess at the beginning at shallow depth. And but still you have some residual anisoplanetic aberrations because we have made I have estimate the aberration in one location and apply the same correction to the whole field of view. And of course, because the probe is finite, you don't have this, the isoplaneticity is not checked over the whole field of view, and so you need to have a local approach. And this local approach allows you to estimate the aberration phase law in different locations. So here are a few examples in the frequency domain. So normally, if you don't have any aberration, this law should be completely flat. And you see that the aberration phase law is thus varying a lot across the frequency spectrum. So it means that you need to address each frequency separately. And for each frequency, you have a different spatial phase law to remove all these reverberations. So this is what we do. And now we have a more perfect image. We remove some secondary lobes we used to have. And so the image, we have improved a lot the image contrast and, of course, the axial resolution. But in real life, it's not so easy. In the head phantom experiment, I come back to this problem. We have strong attenuations, strong aberrations, reverberations, and these aberrations are also spatially varying a lot. So it means that we don't have any isoplanetic effect. So it's very difficult to extract an aberration phase law in speckle because you need to average a lot in speckle because you have many unknowns now. You have to determine all the spatial and temporal degrees of freedom of your focusing law. So it doesn't work in speckle. It only works in for very bright scatterers. So you're able to compensate for aberrations for these specific points, but you're not able to retrieve the good focusing law inside speckle. So to go beyond isoplanicity, just to explain, it's just that now the aberration phase laws are too different inside the correlation area, and we cannot extract this aberration law. So to go beyond this isoplanicity, I will go towards dynamic matrix imaging. So I will explain you what happens. So if you are in a perfect isoplanetic area, you have all your wavefronts, reflected wavefronts that looks like a lot each other. Once you have removed the geometry component, and you get an aberration phase law. If you now consider a more complicated situation, like in the skull, your wavefront distortions are too different from each other, and they don't converge towards a proper focusing law. So now the idea is to consider the reflection matrix at different acquisition times. And now you can hope, for example, in the brain, you have blood, so scatterers are moving, and you can have different realization of disorder just by looking the same point at different times. Okay? And now your wavefront distortions, if you suppose the medium on top of it as static, you can have different realization of disorder, and you can have access to an aberration phase law for each point inside the medium. And then it's perfect because you can get a perfect image based on this information. So to do it in practice, so we come back to the preclinical experiment. We had this experiment with the sheep where we measured a lot of reflection matrix at a very huge frame rate, 200 Hertz, sorry. And then we have access to a dynamic focus reflection matrix for each frame. So each frame is different time of acquisition of the reflection matrix. And so what we can do is to consider this. So this is a B-scan image, for example. And what we do is to extract the dynamics. So if you look at this original image, it does not change over time. But by performing some local average over time, you can extract what is moving inside the image. And if I represent the amplitude and phase of one point, for you to just take this point and look as a function of time, you have this cloud of points. And you can extract what is dynamic in this cloud, really dynamic, really moving at between each acquisition. and you get this very random signal. And now you can use it to extract the aberration phase law. So from this, we can correlate all the reflected wavefront we get at each frame, and we get now an aberration phase law for each point inside the medium. So meaning that you have access to the real transmission matrix between the probe and each point inside the medium. So this map of aberration laws is very complicated. You look at the aberration phase law, it's more noisy than before, because you now address more complex trajectories that are associated with very small isoplanetic patch. And then you can use them to compensate, to correct your reflection matrix. So so here you see some image at different at specific time, and you see you have some bubbles here. For example, this one here. So the signal of the bubble you see is very spread, and now you have thanks to this dynamic matrix imaging tool, you're able to put all the signal at the same around the same point. And so of course it can be very helpful for ultrasound localization microscopy to track and track the bubbles. And so you can perform a power Doppler image to see more what's happening over time. If you integrate the movement over time, you start from this image where you have a gros pâté, I would say in French. It's difficult to see if there are many bubbles on everything. And at the end, you obtain these very bright scatters that are much more resolved and at good position inside the medium. So I see that the Sherman arrived. You can probe the characteristic Doppler frequency to get the velocity. And okay, so I will not go towards the wave velocity, but we can discuss with. Okay, but just to finish with that. So this dynamic matrix imaging can also be used, of course, in seismology, because you can exploit fluid motion, for example, in volcanoes, fluid ejection, and we did that with Michel. And so you can use this information, time information, to really improve your image. And I will not talk about, but we can have discussion about the wave velocity imaging. So how to use the spatiotemporal focusing laws that we extracted to build a map of the speed of sound inside the medium. So here I just consider the example of the liver, where we are able to retrieve the speed of sound in different parts, so in the fat, muscle, and liver. And it's very important in ultrasound imaging because it gives you, for example, in liver, the speed of sound gives you an indication of disease such as steatosis, that are an accumulation of fat droplets. And when you look at the ultrasound image, you see anything. But when you retrieve the wave velocity and map the wave velocity, you can really detect this kind of issues. And it's also true from some tumors in the breast. You can also have, with the speed of sound, you can have a very nice quantitative image of ultrasound. So with that, I thank you for your attention, and sorry for being so long.